In this problem, we want to check for what values of v would this function lie within Hilbert space. So what that means is that we have a collection, a set of vectors, and in this case, all the vectors populating this set are all functions. And then within this vector space, all the functions will be square integrable within some given range. So for some given range a to b, this integral over here should be smaller than infinity. If there's a function that satisfies this property, then that function belongs inside this vector space. It belongs within this set. So what we want to do now is to check for what values of v would this function satisfy this property so that it would belong within this set. So we can say that this function will belong inside Hilbert space. So in order to do that, we're going to calculate this integral over here. And for this case, we're going to be considering the range where a is equal to 0 and b is equal to 1. So we're going to integrate this function from 0 to 1. So considering the integral, we have an integral from 0 to 1, and we have the absolute value square of f of x. So the absolute value square is just the conjugate multiplied by itself, but here we can assume v is always real as given in the problem. So what we have to do is just to square this function. So we have x to the power of 2v dx. And integrating this should be straightforward enough. So we have x to the power of 2v plus 1 divided by 2v plus 1, evaluating this from 0 to 1. So we have 1 to the power of 2v plus 1 minus 0 to the power of 2v plus 1 divided by 2v plus 1. So let's just get rid of this for now. So in order to determine whether this expression over here is smaller than infinity, we need to consider several cases. So first of all, if you consider the case, for the first case, when v is larger than negative 1/2, you can see that there's nothing wrong with this expression. You can just substitute in your number, and then you will get some real number for this integral, and that is surely smaller than infinity. So for values where phi is larger than negative 1/2, the function f of x does lie within Hilbert space. Now a second case is when v is smaller than 1/2. Now if you check out the cases when v is smaller than 1/2, you can see that you will have trouble with this expression over here. So let's say v is some negative number, let's say negative 2, which is of course smaller than negative 1/2. You're going to get 0 to the power of 2 times negative 2, so negative 4 plus 1, so 0 to the power of negative 3. So you have an expression that behaves with a 1 divided by 0, and of course that expression is going to diverge, and then it's going to break this condition. So when v is smaller than negative 1/2, then this function will not lie within Hilbert space. So if this v here is something that's smaller than negative 1/2, let's say x to the power of negative 2, then f of x will not lie within Hilbert space. Now for the third case is when v is equal to negative 1/2, and you will see there's also a problem with this because if you substitute this in, you get 0 to the power of 0, which is undefined. And then we get this strange behavior because if you look back at this expression, we're using this rule to integrate this function, but you can see that when v is equal to negative 1/2, the integral should become the integral of x to the power of negative 1. So you can see if you substitute in negative 1/2, you get x to the power of negative 1. And then we know that for this function over here, if we're trying to integrate this, we can't use this rule. Instead, this is a special case. This is going to be equal to the natural log of x, and then we are going to evaluate this from 0 to 1. And if you substitute the numbers in, natural log 1, that's just equal to 0, and then we have minus natural log 0. Now natural log 0, this expression is going to tend towards negative infinity. So we have negative of negative infinity, so you have infinity. So once again, if v is equal to negative 1/2, then this integral over here is also going to diverge. Then that means this function is not going to lie within Hilbert space. So for this case, your function is also not going to lie within Hilbert space. And so there we have it. This is the condition that v has to satisfy in order for f of x to lie within Hilbert space. Now that's part A of this problem. Now in part B, we need to consider some simple cases. So in part B, the first case we need to consider is that we have a case where v is equal to 1/2, and so using this expression over here, that means our f of x is equal to x to the power of 1/2, or you can also write this out as square root of x. And first we want to consider whether f of x lies within Hilbert space. And this definitely is true, right? Because when v is equal to 1/2, then it satisfies this condition. And then we know that for v larger than -1/2, then this function has to be inside Hilbert space. Alternatively, you can just substitute in 1/2 inside this expression, and you'll see that the integral definitely converges to a number. So that's why, for the first case, the function does lie within Hilbert space. The second case we need to consider is x times f of x, which becomes x to the power of 3/2. Once again, this is rather trivial. Of course, it satisfies this expression. You can substitute this in. You can see the integral definitely converges. So yes, this expression, x f of x, will give you another function that also lies within Hilbert space. Now for the third case, we have the derivative of f of x. And if you take the derivative of this function here, you have 1/2 x to the power of -1/2. So you have x to the power of -1/2. And as we have seen just now, this is not going to lie within Hilbert space. So this expression here does not lie within Hilbert space. So the point of this part actually is to show you that by applying this operator, d dx, you can understand this as a linear transformation if you're familiar with linear algebra. If you apply this transformation to this function or this vector that lies within your vector space, once you apply this transformation, it can actually take it out of the vector space. So before, this function was within the vector space because it was square integrable, but after you apply this transformation, it is not square integrable anymore. So now it lies outside of the vector space. So doing a simple transformation like this can bring a function or a vector outside of the vector space.